Hello everyone. So in this session we are going to study work done in stretching a wire, then working stress, factor of safety and factor affecting elasticity. So let us start with the work done in stretching a wire. So let us consider that a force F is applied to any wire whose original length is L and whose cross section area is A. So if we want to find the work done in stretching this wire. So if we consider small l is the stretch or the extension produced due to the force applied F, then we know that stress is nothing but force upon unit area and strain is change in length upon original length. So stress will be force upon area F by A and strain will be small l by capital L. Small l is the change in length, or we can call it as a stretch, and capital L is the original length. Now Young's modulus is the ratio of stress to strain. So we get the expression for Young's modulus, which is FL upon AL, where small l is the change in length. Now in order to find the work done in stretching the wire, the formula will be dW is equal to F into dL. Suppose we want to find the work done in stretching the wire by the amount dl. So dw will be F into dl. Now to find total work, we need to integrate, or we need to get the summation. So we will be integrating this work dw. So total work W is nothing but integration dw, and integration will be over the length of the wire. Since integration is over the length, all of the other quantities that we get from this equation of Young's modulus. What is Young's modulus? The expression for Young's modulus is F into L upon A into L. Now if we make force the subject from this expression, then we'll get YAL upon L. So substituting this expression of force into this integration, we'll get integration YAL upon L dl. Now integration is with respect to L. So all the other quantities, then small l, will be coming out of the integration, and integration will be just with respect to L. So we know that integration of L will be L square by 2. So the final total work done will be YAL square by L. So as we can see in this equation can also be expressed in terms of force again, since force is YAL upon L. So we'll get the final expression as W is equal to half into force into L, where this L small l is nothing but the extension produced due to the applied force or the stretch produced due to the load. So we can say that work done in stretching a wire is nothing but half of stretching force into stretch. Also, this work done in stretching a wire can also be called as potential energy stored in the wire. So this is the expression for work done. Now we will look up to working stress and factor of safety. So it is observed in all the metals that Hooke's law is obeyed, or we can say Hooke's law hold good up to a certain limit only, into very small region of stress. So there is a need of a safeguard to work with the metals. Usually the applied stresses are kept below the ultimate stress so that elastic limit is not reached. Now the maximum load applied per unit original cross section area within the elastic limit is known as working stress or working strength, or sometimes it is also known as tenacity, and the corresponding load is known as working load. So the ratio of ultimate stress or breaking stress to the working stress defines a term which is known as factor of safety. Factor of safety is the ratio of breaking stress or ultimate stress to working stress. Now there are some points, there are some considerations that should be taken into account to decide factor of safety, such as the static or dynamic loading conditions, whether the load applied is fixed or it is changing, like a maximum expected load to be kept. Now, what load is a maximum expected to be applied on the wire or any body? Then degree of expected wear and tear of material under use. Then possible outcomes of a breakdown. These are the most general considerations that should be taken into account before deciding factor of safety. Now there are also some more beside this. For example, what type of material under the deforming forces is, whether it is a crystalline or non-crystalline, or deviation of the material from isotropic conditions, or the standard of workmanship available, or the boldness of the designer and his preparedness to take risks in interest of a higher output. Now this factor of safety is also sometimes known as factor of ignorance. Okay, so now let us discuss factors affecting elasticity. Now the structure of the material or metal affects elasticity greatly. It is observed in the microscopic examination that metals are just an aggregation of a large number of crystals arranged in a random fashion. However, it is found that a single crystal of any metal showed marked increase under deformation. For example, if a single crystal like silver is stretched up to a bit more than twice of its length, then it is observed that its hardness, or we can say its stiffness, increase 92 times of its original strength. So let us discuss some factors that influence elasticity. The first factor is effect of hammering, rolling and annealing. So due to hammering and rolling, the crystal grains breaks into smaller units that increases its elastic properties. But while annealing means process of heating and cooling gradually. So while annealing, what happens? So annealing produce a uniform pattern of orientation of the crystals in one particular direction that produces larger grains of the crystals, which decreases the elasticity, or we can say increases the softness of the material, or increases the plasticity. So it has been said by Sir Lawrence Bragg that in order to be strong, metal has to be weak, which means that metal with smaller grains have high strength. So metals with smaller grains are stronger than those of larger grains. So the next factor is effect of impurities. Now some impurities are intentionally added to the metals to increase the binding of their crystal grains without affecting their orientation. For example, carbon is added into molten steel and potassium is added in gold to strengthen their elastic properties. So these impurities are added in the metal to increase their elastic properties, or affect their elasticity. Now these impurities either enhance or impair the metals, as they themselves are more elastic or plastic than the metal concerned. Now the next factor is effect of change of temperature. So the elasticity is greatly influenced by the change in temperature. Usually for most of the cases, elasticity decreases with rise in temperature, and vice versa. One of the exceptions is inward steel, that is not affected by any change in the temperature. Now lead is more elastic, or we can say it becomes elastic and rings like a steel when struck by a wooden mallet if it is cooled below a certain temperature. Also, At ordinary temperature, a carbon filament is becomes more plastic. Also, a carbon filament at ordinary temperature is highly elastic, and when it is heated by a current flowing through it, then it can be deformed when a magnet is brought near it. Also, carbon filament is highly elastic at ordinary temperature, and it is heated by flowing current through it. So it can be deformed by bringing magnet near to it. So this is how the temperature affects the elasticity, and these are the most general factors that affect elasticity.